Oh, I need my speaker's notes. I just realized. Didn't see that. Yes, there we go. Okay. So, my name is Brian. I work at Erlang Solutions, and I kind of want to mention that for two reasons. One is this is a talk about Elixir primarily, and Erlang Solutions does quite a bit of Elixir. That's the thing that not everybody knows because of the name. So do know that if you need any help with Elixir. But also, in working at Erlang Solutions, I have a lot of experienced Erlang colleagues who, it's interesting seeing their perspective that in the Elixir world, not a lot of Elixir developers know that much about sort of the underlying things, processes and supervisors and things. And you get exposed to it, but it's still maybe you don't know as much as someone from the Erlang world, certainly. So that's what I'd like to talk about. And to give you a sense of my perspective, I come from Ruby on Rails primarily, a little bit of Node.js, a lot of web development, and so a lot of what I'm going to be talking about today is sort of the web development perspective. It doesn't necessarily apply everywhere. And yeah, so I have a confession that I'm going to start with. I used Elixir for 5 years, and I didn't know what the beam was until someone mentioned it, and I was like, what are you talking about? Is this the beam? So that's fixed now, but in Elixir, you don't necessarily need to. I mean, it's useful, but you don't necessarily need to talk about the beam. You have controllers and channels and live views and all these things hide processes from us for the most part. You have PubSub that works magically, Ecto, Oban, all these things that kind of let you just write your code, right? So do we need anything more? Sort of one question. And this title of this talk could be taken in a couple different ways. Do you really need processes? One way that you could ask the question is, do you need to explicitly use processes? Because of course, if you use Erlang or Elixir, you're always using processes. There's no choice. But do you need to explicitly, figure out and use processes? And people going through a career in Elixir, say, will probably go through a sort of a journey. Maybe starting out with like, oh, I don't know, I'm just trying to figure things out, and then a little bit into it, you're like, oh, absolutely, of course, that's the power of the beam. I need to use processes all the time. But then a little bit further, you're like, well, not all the time. Sometimes it's not necessary and gets you into trouble. And of course, the big brain answer is no, you don't need to use processes, unless of course you do, because the answer is always it depends, right? We know that. So another way to ask this question is, do you need to understand processes? And my answer to that is absolutely, you need to understand processes. You need to understand, ideally, Unicode, caching, you need to understand authentication, dates and times, at least at a conceptual level, right, if you want to be able to debug and use these things, even if you're not like implementing the code that does it. So I really liked this presentation by Chris McCord earlier this year at ElixirConf. And I think this is a really good example of why it pays to understand processes conceptually. Is he works at Fly.io. They were implementing a live view app for administration for users to be able to administer their instances, and they wanted to be able to allow people to export a database from their instance, from their account. But what you might do if you just use a database is you store maybe a one-time token in the database, and then you send that token up to the browser, and then the browser sends that to the controller that actually does the downloading, and then that goes to the database and checks it and then does some logic. And there's a whole little dance, right? But what they were able to do with an understanding of processes is say, like, well, live view is a process, so I could just I could encrypt up that PID along with some other information up to the browser. The browser can send that down to the controller, and the controller could just send a message, GenServer message, over to the live view, and the live view could say yes, and now I'm going to expire that token and just do it the one time, and you don't need anything in the database. So you can simplify things a lot if you understand what you have available to you. But how do you know that you need to? Yeah. So this is this question, like, how do you know you need to use something when you don't really have a chance to use it, right? And I think you get experienced colleagues. Ideally, you maybe try some things out. But I think one really great way is play. Of course, is a great low stakes sort of environment to sort of learn about different things. And I wrote a blog post called "How Far Can I Push a Gen Server," which I recommend checking out. That was really fun to do. And then later on, I'm going to present a little experiment that I did, just try to implement state in different ways in a Phoenix application. So there's this thing that people say about the Beam, that processes are like microservices in a single application, which is definitely a really cool thing, right? Like, I think that's really cool, but also maybe a little scary, because microservices are also something that's hard, and they're something that's complex, right? And so microservices to me are like something like macros, right? You should have a good reason for using them. You should be a little afraid of using them. You should kind of ideally know what you're doing, and right, but again, you can't necessarily know what you're doing until you've tried it out and gotten some experience from it, right? But at the same time, processes in Elixir, they're much lighter weight. Individually, the messages they send are much simpler, and you're just passing in memory, which is all of this makes it, of course, simpler than creating microservices. So I think it's almost kind of like microservices, but nice, right? And as much as microservices, as much as the Beam makes it sort of like microservices easier, it doesn't make it easy, right? We're still dealing with concurrency. We're still dealing with things happening at the same time, and that always is something that can bite you in the butt. So today I want to talk about, I guess, two parts of this talk. I want to give perspective on a couple of different things, specifically resilience, the idea of resilience, the idea of state. And then I want to, again, what I said before, present the results of this experiment that I did, just trying to play around and see what I could do. So resilience can mean a lot of things, right? It's fuzzy. It can be hard. Like, what does it mean to be resilient? And it's often something that's not defined when you're doing a specification of your app, right? It's just like, yeah, of course it should work, right? Don't let it crash. Well, let it crash, but. So here's an example of a mall with this big display on the column, and I'm sure it looked very pretty at one point, but if it crashes, then you get this very funny, sort of embarrassing thing, right? And it didn't catch fire, but maybe if it had just turned off the system when it failed, someone could eventually fix it, but at least it would just be black, right, or something like that, right? So that might have been a little bit better, but it wasn't maybe part of the specification. So I always think I love this graphic from this blog post called "Resilience versus Fault Tolerance." Definitely recommend it. I think it's a series, and I actually appreciated a lot of his posts when sort of researching this. But he talks about how resilience in IT systems should be thought of as a socio-technical system where you have the software that you're writing, and then you have the people and the processes that are around that thing. That's super important, and even the software is oftentimes a small part of it, right? And maybe we can push that open and make software be able to do things that it couldn't do before, and resolve things that it couldn't do before. But you can only get up to the point of the screen or the printer or the keyboard or whatever, right? You're limited in what you can do, even though as software developers, that's what we think of all the time. So it kind of feels like the whole world, right? So one example I encountered recently was I was getting a passport, and I booked in an appointment and put in the booking number to the kiosk when I got there, and I was supposed to get a ticket, but on the screen it was just a blank, and I didn't get a ticket, and I was so confused. And the person came behind me, and they got a ticket, they got a number. I was like what is going on with this? And so I just thought for a few minutes. I was like, not sure what to do. So I hit the general information button. That gave me a ticket. Okay, and I went up to the person at the desk, and she helped me right then and there, and it worked fine. And to me, that's resilience in a socio-technical system, right? Like it's thinking about the whole, right? And it's thinking about the kiosk didn't crash. It still was able to handle the next customer still, even when a problem happened. And there was an option for me to sort of do something else. And the person had training, they had experience, and they had flexibility to deal with the situation. So it all depends on your use case, of course, but these are the sorts of things that you want to think about. You might know about this. This is called this is an example of the Swiss cheese model. It's the idea of when you think about a system, you want to think about all the different things that can go into it that might potentially keep problems from happening. This is an example of a pandemic response that you might have for disease prevention, and each layer, nothing's perfect, right? Everything can always let a problem get through, but the more layers you have, the more chances that, less and less chances that there are going to be holes that line up that allows some problem through, right? So if we think about a Swiss cheese model in terms of software development, some very simplified model might be this a model where we have some automated testing, we have some manual testing, and then we have supervisors that can deal with some of the issues. And that's not going to get everything, but it's going to stop some things, and then that's going to maybe make it less often that we have to wake up at 3 a.m. and have to deal with an issue, right? So that can also be a whole bunch of different things. You might have a bunch of different slices in your Swiss cheese model, right? You might be designing very carefully at the beginning so you don't have any confusion about what's supposed to happen. You might write clean code so that it's less likely you'll get bugs. You do code reviews, of course, are great. Metrics and alerts don't stop bugs from happening, but maybe they allow you to fix them before users have even noticed them. So, I consider that all part of a good Swiss cheese model. So I want to talk about this idea of let it crash, right? Because we talk about this quite a bit, and it's a great phrase that catches your eye. But I talk with some of my colleagues at work, and we talk about this idea of maybe it should be called let it crash responsibly, right? Super boring. That would not have caught on the same way. But it's kind of more true, right? But I think that even that doesn't quite unpack it right, and I think that it's worth exploring some. Again, at that same talk with Chris McCord, he talked about this idea. I'm going to just read this. We promote let it crash. You code only the happy path and you don't have to think about errors. It's really nice because if things crash and it restarts, it gets back to a good working state. All that's valid, except when you have a user on the other side, right? You kind of have to think like what you're dealing with. You can't just let it crash, right? Live view crashes and it gets back to a good working state, but that's still disruptive to your user. Maybe they lose some data or something happens, right? So you can't just let it crash. So in thinking about this, and trying to figure this out, I was looking back at Joe Armstrong's thesis from 2003. And he wrote, when we program, we want to structure the code into the difficult and easy modules. The difficult modules should be few and written by expert programmers. The easy modules should be many and written by less experienced programmers. The generic component should hide details of concurrency and mechanisms for fault tolerance from the plugins. The plugins should be written using only sequential code with well-defined types. And so in this, he was talking about OTP, he was talking about GenServer. The gen in GenServer means generic, so this is just what he's talking about. And they realized, that you can't just do send and receive all the time. You have to have some sort of abstraction, right? So it's super easy for me to see this and be like, oh, that's what Phoenix is doing, right? You're encapsulating some of the complexity that you don't have to deal with all the time. And I think that's true to some extent. But it's higher up. It's a little bit different, right? In GenServers, you're still dealing with processes. You're still having to understand some of these things. But I think that this is really interesting. It's an important way to think about this. And he also talked about let it crash specifically. This might be where it came from. I'm not sure. But he said, by this I mean, in the event of an error, then the program should just crash. But what is an error? For programming purposes, we can say that exceptions occur when the runtime system doesn't know what to do. Errors occur when the programmer doesn't know what to do. And I really love this distinction, even though you can draw it arbitrarily. I love having a distinction to say, like, okay, an error is something when the programmer doesn't know what to do, like the specification didn't define it. And in the thesis, he talks about well-behaved functions in this sort of generic versus specific situation, and that the well-behaved functions are the things that you implement, that you take care of everything that you can if you know what to do with it. If an exception comes up and you know what to do with it, you deal with it. But if you don't know what to do with it, that's when you let it crash, and then you let it recover, right? As sort of this backup. That's also still a little bit, to me, fuzzy as to like, okay, when exactly do you do this? I know it depends on the situation, whatever. There's this other idea in the thesis that I really like, that I think also is a clarifying thought for me, that one of the basic elements of system design is identifying which parts of the system have to be correct and which part of the system does not have to be correct. The first part of system design is to identify the part of the system that must be correct, and we call this the error kernel. That's like, so it's the idea that you can pick out a part of your system and be like, okay, this always has to be correct. I can depend on this, and then other things delegate. And he draws a parallel with operating systems being assumed correct, and then applications will run, and they may or may not work, right? But you can always depend on the operating system. So I think this is a really useful idea, and I try to think about this in designing Phoenix applications. I feel like if you have a controller in a Phoenix application, Phoenix is kind of your error kernel in that situation. It's taking care of things for you. If something crashes, it'll catch the exception and deal with it. Whereas if you're dealing with live views or channels, those sorts of things, those are where you're sort of taking on more responsibility to make sure that things are working for the user, and you might be thinking more in terms of an error kernel for those situations. I think also the async assign thing that was added to live view recently, I think, is another example of like how it's another tool in our toolbox to make a live view, for example, something that's more of an error kernel type thing. Another thing I think it's important when trying to think about like what do I have to make important, what do I have to make an error kernel, and what can I be a little more loosey-goosey with is trying to think about the different types of data that you have in a system. This is from a blog post, this idea of you have scratchpad data, and that's just something where like you don't care about it. If something restarts, it goes away, and you just start again. It's like you might think of like a blackboard in a classroom, right? Between classes, you reset that. Static is something in this definition is something more like if you have a TCP connection that comes in, maybe you got that from the initialization state from your supervisor, and then when you need to restart, then you have that again, and so you've held on to it. And then dynamic is another type, and it was just sort of split into recomputable and user supplied. Recomputable is almost kind of like scratchpad data. It's generated from something, and so if you need to regenerate it again, that's not a big deal. But user supplied data is the sort of thing that's like, if you have user supplied data, that's what you have to really hold on to. You have to like think about how you can protect that and make sure that it doesn't corrupt and over time. So that's where you might like have I think even the part that I didn't read and about that Joe Armstrong talked about the error kernel was talking about how that's where you sort of keep your state and keep the thing that you really care about in the error kernel. One thing I guess has sort of been in my head is like this idea that a Phoenix controller recovering from exception isn't really special, right? It's, to me, coming from like Ruby on Rails, it's just something, your server's not going to crash just because there was an exception, right? That would not be a good web server. And in Phoenix, you don't really use anything special to recover from a controller exception, right? It just catches it and displays your custom 500 error. So, this is all kind of what I was talking about before, like controllers, live views, like where do we sort of deal with these sorts of things? And Phoenix, I think, is also sort of an error kernel in some cases in general, and it's okay to have, I think, nested error kernels to sort of, again, it was almost kind of like a Swiss cheese model, right? You're sort of protecting things within things. And then last thing on resilience is this idea that I was struggling with for a while when I was coming up with this talk. I was thinking, like, why exactly would you put something into a process to recover from failure when you could just catch an exception, right? Like, what's the difference? Because they are different things. It's like, why are these different, and how are these two different tools that could be used in two different situations? So some things that I came up with is that if you have you can have multiple processes listening for an exit. So if something fails, then multiple things can recover from that, and that's kind of special. You can't really do that easily with an exception, right? You could have one process listening for many things, so that's also pretty cool, right? Supervisors, of course, are the primary example of this, but you can do this on your own. There's nothing special about that, and nothing special about supervisors, really, except that they're just a lot of code that dealt with a lot of situations that you don't want to have to deal with. And then you can choose to either choose link for structural relationships or monitor for non-structural relationships, so you can use these tools to sort of fit your use case and sort of deal with situations in a sort of more solid way, right, using the underlying tools. And then one thing that something I hadn't wrapped my head around that I think is an interesting idea is that if you're trapping an exit message from a process that dies, you don't deal with it right away. There's a signal, you'll get the signal comes in right away, but then that queues up a message on your mailbox. And if you have a bunch of things in your mailbox, you'll eventually get to that message that tells you that the process died. So it just becomes a regular message, and so you can deal with it in your own time, which I think is also, again, that's not an rescue an exception. Rescue an exception happens immediately. So resilience, talking about state, which is related, I think. I think maybe all of this, I think we don't talk enough about these things, but I think we could talk a little bit more about state, in particular in Elixir, and especially how it relates to Erlang and coming from Erlang. Again, going back to Joe's thesis, he writes that software architectures are not general purpose, but they're designed for solving specific problems. no description of an architecture is complete without describing the type of problem that is supposed to be solved using the architecture. So hopefully this is something we're doing all the time, right? Like we're thinking through like, I'm using Elixir because it's the best fit for my job, right? Or not because it's just the language that I love, right? But in talking about how Erlang was written for telecom systems, he lists out the 10 things that make it a good fit for a telecom system. And he even wrote that many modern internet services, for example, web servers, would have a strikingly similar list of requirements. So this is 2003, almost 10 years before Elixir came along. Joe kind of knew what was up, right? But I feel like there's a couple of here, in my opinion, that don't fit quite as well. Web servers don't usually control hardware. They might, but not usually. But a big one is that software maintenance should be performed without stopping the system. That's a big one that doesn't apply a lot in, I don't know if I'd say modern, but a lot of the web applications that might be developed these days. And that's a difference, I think, that's worth understanding. There's hot code reloading, right? And it's something that Elixir supports, but it's not used very often. So if you were going to use it, you'd probably be forging your own path to some extent and figuring some things out. There are kind of already ways to deal with not having downtime when doing deploy. You have blue-green deploys, these sorts of things. So it's like, okay, well, we kind of don't need it for that respect. Some teams might not be comfortable with it. Might be like, what is this thing? If you have a DevOps team that you're working with, they are probably working under the assumption that they should be treating server. A lot of times you should be treating servers like cattle instead of like pets, right? Because you want to be able to just kill a server and replace it if there's a problem, right? And that's something that doesn't fit with holding things in memory, essentially, right? You also might have an organization that has a lot of different languages, that different teams are working with different languages, and you might have some standardized deployment that you have to go with, right? Maybe you have to put it in a Docker container and deploy it out, and you could still do hot code reloading, but it might still have some friction there. So I think a lot of this depends on the fact that a lot of times we basically just depend on a database, right? It's kind of been a fait accompli of web applications for a long time, is that you have a database, it's always there, you just kind of depend on it, and the web application can go away, and when it comes back, it'll just have the database available to it, which I think is not quite where the Erlang world came from with using processes and ETS and amnesia, and a lot of times you have long-running systems that have things in memory. So it's a very different world, and so in Elixir, you are probably talking a lot more about like processes or things that are used for temporary data. You have to think about what's going to happen on the startup of my application, or like the first access of trying to do something, or if you're shutting down an application, like what am I going to do with this, this data? And so it's a different world. And yeah, so different role. Different Elixir, sort of a different thing. So on that note, I have this experiment that I did. The idea was to create an application which was sort of a basic simulation of a ride-sharing app. You think like Uber or Lyft. Not nearly as complex, but just to try out, like, okay, let's say I have some drivers and I want to, benchmark some different solutions. With this realistic use case. So this is a live view page that's just showing a whole bunch of drivers moving around. So all the drivers are external to the application. They're sending updates and saying, okay, now I'm here, now I'm here, now I'm here, now I'm here. And then occasionally updating their state to say that they're ready for passengers or that they've gone offline. So that's what the color changes are there for. So that's the idea of the application. To clarify, this is not like the scaling to 2 million channels sort of thing. That was awesome, but these are doing some more work than that was using a smaller machine. The goal is not to scale as high as I possibly could. The goal was just to compare some solutions here. So to do that, I, using my laptop, I had just an M1 MacBook Pro. I limited myself to 2 schedulers just to kind of have a baseline. It's still parallel, but it's not crazy. I was sending some stats-D measurements so that I have some charts that I'll show, and that all my data that I had for this came through stats-D metrics. And then, as I was saying, the drivers are external. They're sending updates about their position, their current state. And then there's also a request that sends a request for just the driver's current state, which is kind of unnecessary, but different solutions will have different strengths and weaknesses based on read and write characteristics. So I wanted to be able to test that. And the first thing I tested was sort of more write-heavy, and I'll get to another aspect of that separately. So first sort of stab at this, had a database. That's the simple, out-of-the-box solution in Phoenix. So how far can I get just having drivers update themselves, or update their position a whole bunch? And I got up to like 13,000 or 15,000 driver connections connected, which is pretty good. Like not a lot of, and it's even more. I think I was like 28,000 requests per second in various channels. So like it's not. Like very few applications that I've worked on in my professional career have needed more traffic than that, right? And so there's a reason that the database is kind of the go-to solution, right? It often works, and this isn't even tweaked, right? Like when it would fail with this exception that maybe you've seen from the DB connection library underneath Ecto, where it's saying basically requests were queuing too much for too long, and so it just started failing. And I could have tweaked this. I could have changed these timeouts and these numbers, but I wanted to sort of just keep it at a base level for this particular experiment. So, but database probably could have gone at a higher scale. If I tweaked Postgres, tweak the configuration, probably could have gone even further. So the next thing I tried was the database, but with a individual record store in front of that, as sort of a cache. So each driver has a process assigned to it, and it has the current state. And that didn't go that much higher, but maybe that's not particularly surprising because it wasn't very read heavy. So we'll get to that in a minute. But it was it's a little bit the higher end. It was not doing too bad, but it didn't help a ton. The positioned record store was another state solution that I tried, which was basically just one process that had a big map of all the drivers. And then it handled all the requests with that one process. And that did quite a bit better, maybe not quite 2 times better, just kind of because everything was in memory, everything was pretty quick. But also you might be thinking that this is not like a persistent database, right? Like this is kind of what I'm saying. Like if you restart this server, you're going to lose all your drivers. So you would probably want to have some sort of solution that you're sending off state on a regular basis and then persisting it once every few seconds or something, right? Depending on what your needs are. In the needs of a play application, I'm just testing like the states. So, and then I tried ETS, which is, let me go back. So this is actually maybe a little bit worse. This was using an ETS table, but sending messages to a process that's doing the ETS work. So it was a protected table, so only the process could make changes to the table. So that was maybe a little bit work because there was ETS and messages sending to it. I'm actually not entirely sure, but when I switched over to a public ETS table, then any process could work on that table independently, and so that it got up to the highest level that we've seen before, but not really that much further, which is maybe a little bit surprising. And then the last thing that I wanted to try was the partition record store, which is basically just using the partition supervisor that's built into Elixir, which is this cool idea where I think about it like maybe like an accounting firm where each accountant has a bunch of accounts that they work with, and so in a partition supervisor you might have 2 or 4 or whatever processes, each one which has a set of drivers, let's say in this situation, that they're responsible for, and using a hash it always redirects the request to the appropriate process. But that didn't really help all that much with these writes. So let's look at reads, because that does make a bit of a difference. So here I was basically just trying to scale reads relatively quickly to see what would happen. And I was able to do it, since I did it quickly, I was able to do these all in one big go, all right next to each other. So you can see that going from the database here, that was the lowest and the worst performing, and then going up to having a record stored in front, that helped quite a bit with reads, which isn't surprising. It was basically just able to scale across all the schedulers. Position record store did even better, just because everything was just in memory. ETS even better, ETS public even a little bit better, so that kept going up. But then the partition record store actually didn't do as well as ETS, or even maybe it did about as well as a single process, which is a little surprising to me. And I looked into it a bit. I couldn't figure out exactly why that was. Because you would think with 2 processes and 2 schedulers, it should do twice as well as a single process. That is not quite what I found. And so to sort of sanity check that, I enabled 4 schedulers on the system so that I could have 4 partition supervisors. And that did improve things a bit, but not even like twice as much. So I think there's something going on there that I don't probably quite understand. But it was interesting nonetheless. Again, this is sort of just an experiment. Yeah, so I think there's more to explore. I had some questions, but this is where I got for now. And if you'd like to check out the project, it's at that URL. It's called When to Process, because that's just the first thing that came to my head. And that's my website. So thank you very much.
We have time for questions. Maybe I will start. Could you give us some real-world examples where to use processes and supervisors?
Yeah, I think that's I could say like you could do it like an import or export of data, right? You could have like a live view and just say, hey, I want to import some data from an API or something. But at the same, that could also be just like an OBON with a pub sub going on. So I kind of feel like it's something I struggle with a bit, but like it would work if you were doing like if you had a game with a massively multiplayer online game or something, which has a bunch of state, which a bunch of like updates coming in, and all the updates also have to go out to all the clients, and so you have a multiplicative problem. That's probably a great situation because you don't have to go to the database and then do a bunch of database reads, right? Or just things like chat applications, things that you kind of need real time, but you could sort of make the trade-off and persist in a eventual consistency sort of way. Then, but yeah, you always have to think about that. Like, it also kind of depends on how often you restart. Like if you're restarting once every month or something, then it's like, okay, that's maybe something you can get away with. But a lot of times in places I worked, you have to restart multiple times a day. So yeah.
All right, I don't see. Oh, yeah, there is one.
Hi. You do ETS, but now I've got persistent term. Did you try any tests with that?
Sorry, say that again. Oh, with
The Erlang persistent term. Did you try testing that for performance? Or would you expect it to be different in any way?
I might not know what that is. So I know that there's Erlang term storage is a thing, but then when making the table, I put it into like tuples that got saved to ETS, but you're probably maybe talking about something else that I don't know about.
I forget what OTP it's in, but it's relatively recent persistent term.
Oh, okay.
So maybe you haven't seen it yet, but it's supposed to make it's a very simplified way of just being able to store state without having to worry about having setting something up first for the ETS.
Okay. I will look for that, but if you can figure out what that is, maybe share it on Huva or something, and then I'll look later. Oh, yeah. We're code beam, so someone's gonna know.
Okay, yeah, so persistent terms, it's relatively new. I think it's been for a couple of versions anyway. But it's a way of storing data which you want to be able to access by many processes, but without having to copy things backwards and forwards. But, and there's an extremely significant but, it's very good for reading, but if you update or delete things, that is extremely costly. So if you update a term in that, you could basically force a complete garbage collection of the whole system. Right. So for some things it's extremely good, but for some things it's extremely bad. And if you read the docs, it tells you about this, when not to do it. Don't update things, don't delete things, right? Basically, that's what it's saying. So I think for Brian's case, it would not be usable.
Yeah, maybe for like that second use case where I'm doing like a whole bunch of reads.
Yeah, that would do, but once you change something, it's very bad. But typically, if you want to use configuration data, put it there. because you don't change that. But as soon as you change things, you pay enormous cost for it. So yeah. The final thing there is it behaves as if you weren't mutating or sharing data. Okay, so that's why if one process changes its data, none of the other processes will see it because they'll have make their own copies of everything. Right? So yeah.
Cool, thank you.
Okay, I think that'd be it. Let's give Brian another round of applause.